Cool. Hi, everybody. So today we're doing topic 22, linear algebra. And right before this recording, I was saying that I do want to preface today and tomorrow's study group with the fact that there's a lot of math. And yes, it is good to know. And also, if you want to pursue a career in like machine learning and writing algorithms, it is important to understand the math that goes behind all of these algorithms. But in a boot camp, a lot of the time, your understanding can play catch up to your implementation. So to be honest, all of the stuff that we're talking about today and tomorrow, you will probably never do for the next, honestly, for the next year. You probably will not touch this stuff directly. However, if you do want to, pursue a more technical, like data science or machine learning role, it does become more and more important because the higher you get, the more you're expected to understand. So your understanding will play catch up to your implementation. For example, today, what we'll be talking through is how stats models actually does, solving the coefficients for your linear regression. And tomorrow we'll actually talk through how scikit-learn does it, and they're different. So just so you know, if all of this is like going over your head right now, absolutely fine. It's not a big deal because I think like linear algebra is in itself a college course. Yeah, I took like 2 semesters of linear algebra in college, and calculus, as y'all know, there's calc like 1, 2, 3, and that's what we're doing tomorrow. We're like hitting a little bit of, I think we go like calc 1 and some of 2. So it's a lot, but you're not expected to recreate any of this stuff. So I just want to preface with that. But cool. Linear algebra. How linear algebra is used in the data science space and in the machine learning space varies. There's a lot of different ways you can think of how to implement linear algebra. I'm going to talk through some of those in the why linear algebra section. But whenever you're thinking linear algebra, the first things that should come to your mind are the data types that you use. And those are, for the most part, vectors and matrices, which we'll talk through as well. So we'll talk through why linear algebra, we'll talk through those data types, vectors and matrices. We'll talk really quickly through systems of linear equations before getting to exactly how stats models solves our linear regression with linear algebra. So why linear algebra to begin? It is the basis of many machine learning models. Anytime you're doing things in multiple dimensions, and for us, each feature is a dimension. Every time you are doing something in multiple dimensions, probably what's going on in the backend, you're doing some sort of linear algebra, because for you to apply functions across across a large feature space, you need to do it with matrices. And tomorrow when we get to gradient descent, through calculus, you're actually combining linear algebra with calculus in order to, gradient descent across multiple features at the same time. So that is the basis of machine learning models. And data in itself, a lot of times we deal with two-dimensional, 2D in terms of how it looks data. We have a bunch of rows and columns, tabular form. So by default, data is already set up as a matrix. So you can see rows and columns. For us, this is the Iris data set actually, or in Cantor data set, where we have 4 features, 1 target, but it's in a matrix form. These will actually hit in the next phase, and I'm actually very excited to get that as well. It can be used to model complicated things like language. We'll get into more vector stuff in a little bit, but as a really quick preview, this stuff here is this relatively newer field of natural language processing known as word vectors. And the relationships between words can be actually represented by vectors, which is really interesting. So you can sort of see how like the blue to purple direction, they're both kind of parallel, modeling the relationship between man and woman to king and queen. So it's pretty neat that like the direction of going to man to woman and king and queen are kind of parallel to each other because you're modeling the direction of that change. This is kind of like analogies. I think that's what the SAT thing was. So very, very similar then. That's actually really cool. We'll get to that towards the mid to late part of phase 4. Same for tenses. You can also model tenses in terms of vectors, and also to some extent named entities. So you have country capitals. So the capital of Spain is Madrid. The capital of Italy, Rome. I didn't know that. But yeah, it models all sorts of relationships when it comes to words, and those are super interesting. And these are all vectors. Another application is images. So we're actually going to work with images in phase 4 as well. And basically every image is represented as either a matrix or a tensor. So if you think about every image, this is actually what an image is. So here we're zooming into like, what's this, 8 by 8? Yeah, we're zooming into 8 by 8 pixels within this image. And you see how each pixel has an intensity of, I guess this is a black and white, it's a grayscale. Yeah, it has 64 squares represented by a 8 by 8 matrix, where each number determines the intensity of how black or white the color is for that pixel. Now for a color image, if you've heard of like RGB, it's RGB because you have a tensor representing the image, where instead of just, one, this is for grayscale, instead of just having one layer, you actually have three matrices layered on top of each other. And those 3 matrices layered on top of each other, one is red, one is green, one is blue, combined together, you have an image, a color image. So images are represented as either matrices if they're grayscale or tensors if they're color. So very, very neat. We'll actually get to playing around with these data types in phase 4 as well. Finally, this is actually my favorite application of linear algebra is in recommendation engines. This is very, very neat. One of the algorithms that Netflix is inspired by, they don't actually use it, and we'll get to that also in phase 4, makes use of linear algebra too, in terms of how they can get the relationships between what you like and what other people like and combine them all together and provide recommendations. Linear algebra is actually all that goes behind it. And we're actually going to break down that algorithm specifically when we get to that stage of phase 4. Also, I found this meme on Facebook. I thought it was pretty funny. This is kind of like what we did, I feel. So we started with like a little bit of statistics, which is down here. And then we pretty much skipped these and went straight to scalar, not linear modeling for linear regression, even though we have linear algebra and multivariate calculus here. So this is also important because as I mentioned at the start, linear algebra is a basis of a lot of ML models. But yeah, all these use cases, we will hit each of these in the next phase. Cool. So linear algebra, we have 4 main data types when we're talking in linear algebra terms. I mentioned vector when we talked about words, matrix when we talked about just the representation of data, tensor when I talked about the layers of matrices. So scalar is just a single number. So you can see how the dimensionality kind of expands. So scalars only have a magnitude. So literally a number is a number. A vector is an array with magnitude and direction. And I'll talk about what that means in a little bit. The coordinate of I guess right now, the coordinates of a vector represent where the tip of the vector would be if you travel from the origin, and the magnitude of a vector would be its length in space. So to illustrate what that means is, let's say I have this feature space over here, and I have a vector 2, 3. If I have a vector of 2, 3, that just means that we're moving 2 in one direction and 3 in another direction. And of course, if you expand this into n-dimensional space, you can move in all sorts of directions. Of course, we can only perceive up to 3D. But yeah, that's what that means. And let me just label this real quick. This is a vector of 2, 3, and this would be 2, and this would be 3. Not to scale, but that's what a vector means. So that's a vector, and a matrix can be interpreted differently in different contexts, but it's often used to represent multiple simultaneous vectors. So we'll actually see that towards the end of this notebook, how linear regression is solved is it actually treats each row as a vector, which is really neat. And a vector or a matrix can be multiplied by a scalar to create a change in scale and or direction. And as we talked about with images, tensors are just matrices with the same dimensions stacked on top of each other. When you're doing anything in linear algebra directly in Python, they're represented by NumPy arrays, not lists, so don't forget that. We can use the dot shape to explore the dimensions of these data structures. So here you can see I have defined a vector, 2 matrices, and a tensor. Here we can take a look at their shape. So vector shape, you can see it's 6, nothing. Now this is different from 6, 1. So please take note of this. You might hit this when you play with scikit-learn a little bit more, but there is a difference between 6, nothing and 6, 1, because 6, nothing is a vector. 6, 1 is a 1 by 6 or a 6 by 1 matrix. So take note of that. So here's a matrix with shape 2, 3, another matrix with shape 3, 2, and here's a tensor. You can see there's a lot of nesting going on here. So you can see, imagine if I had the images, I had like 4 pixels here over 4 pixels there. That would be a tensor. Cool. And you can also index these just like you index your list, your nested list, the same way. So you can mess around with that. Let's see what, no, there's no 2. We do this, we can go into the nesting of it. That's how you index any of these linear algebra data structures. One other thing I mentioned earlier is the magnitude of a vector, which I wish I could move this drawing here. Let me see if I can do, okay, just for now. So magnitude of a vector, as I mentioned up here, magnitude of a vector would be its length in space. So this formula over here might look kind of familiar. It's basically Pythagoras' theorem, but in more dimensions. So the magnitude, which this is actually the numpy function to get the magnitude, is taken with this, this formula. So basically square root of 3 squared plus 2 squared, Pythagoras theorem exactly, and you end up with the length of this vector. So if I have the length of the vector 1, 2, 3, 4, 5, 6, I can find the length of that, and it's around 9.54. So just in case you ever need to find the length of a vector, just know that NumPy has a lot of these linear algebra things built in. Cool. Now transposing, I don't think I'll need this drawing anymore. Okay, cool. So transposing basically reverses the shape order. You might have already played with transpose when you were maybe cleaning up some data, I don't know. But when you transpose something, it basically turns rows into columns, columns into rows when you're dealing with a matrix. So here you can see with this cell run, we have matrix 1 being 1, 2, 3, 4, 5, 6. And when I transpose it, you can see this is matrix 1.transpose. It just turns each row into a column. Now, if we want to scale up from matrix to a tensor, so not as straightforward as rows and columns, because there's also like layers of these rows and columns. You probably will never have to transpose a tensor because mathematically it doesn't really do anything useful for us. But just know that it reverses the shape order. So if I started with this tensor over here, which is 2 sets of 4 sets of 3, it just reverses the order. So it becomes 3 sets of 4 sets of 2 when I transpose. And you can sort of see that the numbers don't really follow any pattern. Well, it follows a pattern, but you can see that it goes like 1, 2, 3, 4, 5, 6, the exact order of how it's transposed and where the numbers go, not important for us at all. But just know that if you want to transpose something that is in a larger dimension than a matrix, you can do this. Okay. Any questions about these data types before we talk about operations? Okay. So let's talk about addition and subtraction to start. This is the easier one. So for addition and subtraction, matrices, for vectors, matrices, and tensors, as long as the dimensions are equal, the operation is done element-wise. So if I have these 2 vectors over here, 2, 4, and 3, 2, it's an element-wise operation for addition and subtraction especially. So it'll just be 2 plus 3, and then 4 plus 2. And if I, oh, actually, let's put plus. If I run this, you end up with 5 and 6. If I were to do subtraction, exactly the same. Now this element-wise action, if it is, as long as it's the same number of dimensions and the same number of values, it will do it element-wise automatically as an array. Cool. So graphically, what does this look like? So let me redraw my graph again real quick. So element-wise, that's what's happening. Okay. So let's just say I start with an array 2, 4. So not array, vector. Cool. So 2, 4 means I'm going 2 in one direction, 4 in another direction. Let's just estimate that that's here. So this is 2, and then this is 4. So let's just say that this is dimension 1, or dimension 2. Maybe feature 1, feature 2. Interpret it however you think makes sense. So this has moved 2 in this direction, 4 in this direction. If I do plus 3, 2, you can sort of think of it as a continuation of this vector. That's how I like to think of it. So if I'm doing 3, 2, in addition to this, I'll just plus 3 on this end and then plus 2 on this end. And that will result in another vector. Oops, I meant to draw an arrow. Let me just get that arrow in. Cool. So this will be the resulting sum. And that's how you get to, switch these drawing tools. This is how you get to 5, 6. Say this is roughly 6. Cool. And another way you can think of it, some people like to think of it, I don't know if you've done, I don't know, high school, like AP, I don't know what kind of math that is. But anyways, some people like to draw this as well to represent the sum of 2 vectors. Now, if it's minus, same thing. You would just go the opposite direction. If you're taking this vector minus this one, this arrow will just point backwards. And where you end up is what the subtraction result is. Cool. So addition and subtraction, again, as long as the number of values matches and the dimensions are the same, you're all good. All right, so next, broadcasting. Now this I talked about when we introduced NumPy back in phase 1, but NumPy arrays, why NumPy arrays are much more powerful than Python default lists is because they support broadcasting, which happens when you perform operations across arrays with different number of dimensions. So what NumPy does is it makes a duplicate of the lower dimension array. As long as the higher dimension array contains the same shape to execute the operation. And we'll do a quick example here later. And the order of the dot shape tuple does matter. So let's take a look at this quick example first. So in this example here, so let's say we started with the scalar 4. We have the vector 1, 2, 3, 4, 5, 6. When we do vector plus scalar, what NumPy is doing, it is broadcasting this plus 4 onto every element of the vector. So you can see what that's what I mean by here. It duplicates the lower dimension array to execute the operation. It does this plus 4 to every element of the vector. Cool. So let's take a look at matrix 1 and vector 1. Oops, did I not run this first cell? Okay, never mind. Oh, it's down here. Okay, so we have matrix 1, which is 2, 3, vector 1, which is 3. So matrix 1 and vector 1, note that matrix 1 contains the same shape as vector 1. It contains groups of 3 already. So therefore, it basically is making a duplicate of this 1, 0, 1 and doing this action of matrix 1 minus vector 1. So you can see it's 0, 2, 2, which is 1, 2, 3 minus 1, 0, 1, and then 3, 5, 5, which is same thing for the other vector with it. Now, what wouldn't work is if I changed matrix 1 to be something like this. If I changed matrix 1 to look like this, is that all right? Cool. You end up with operands cannot be broadcast together with these shapes because matrix 1 has groups of 2, but you're trying to force a 3 on it. NumPy doesn't know to rotate that 3 and do that operation differently. So something that's good to know. So something to think about at this point, what shapes of matrices and vectors can be broadcast onto this tensor over here? Here's something to think about. Okay, so next let's talk about multiplication. And there's actually 3 different kinds of multiplication that you can do with matrices and vectors, but we're gonna talk about a quick one. The main one is this second one, dot product, and we're just gonna very quickly talk about cross product because we're not actually gonna use cross product almost at all. So Hadamard product, which is the name for element-wise multiplication, same thing as what we did for addition and subtraction. So Hadamard product, you can see that we have this 1, 2, 1, 2 array, we multiply by 6, it does that. But also if we had this array here times empty dot array, this one over here, you can see it's doing element-wise multiplication. It's doing 1 times 3, 2 times 4, 1 times 5, 2 times 9. That's how you get 3, 8, 5, and 18. So Hadamard product, exactly the same element-wise. Again, the dimensions have to match for that to happen. if not, broadcasting will occur if possible. The more important multiplication, which I don't know if anyone has seen this before in like prior math, dot product. And that's otherwise also commonly known as matrix multiplication. So unless otherwise stated, multiplication refers to this kind of multiplication. So what's happening here is you're actually taking the rows of the first matrix and doing an element-wise product with the columns of the second matrix. So let me break that down. Hopefully this will be helpful. But for the first matrix, an order does matter when you're doing matrix multiplication. You're going to take the rows of the first matrix. So you're going to take these sets of values over here, multiply them by the columns of the second. So the columns of the second will be these. So, okay, let's just take a look and see how this is formed. This first value over here, let's go with, let's pick a color. Let's do this blue color. So let's say this first value over here is the first row and the first column. So you can see A11 and A12, A11 and A12, B11 and B21, versus B11 and B21. And you're just doing an element-wise product there. And then you sum it together. So this does take a little bit of time and practice. You probably will never have to do it by hand unless you're interviewing for a slightly more technical role. But yeah, if you are doing that, I would say just sit down and do some examples of matrix multiplication. Could be helpful. So just things to know. What are the shape restrictions to doing matrix multiplication if this is the case? If you want to multiply the matrices A and B, where the dimensions of A are m by n and B are p by q, what are the shape restrictions? Basically, because the number of elements in each row here have to match the number of elements in each column there in order for this to be done successfully, n has to be equal to p. That's something to remember. Cool. So we never have to do that by hand in Python. You can just use np dot dot. Couple ways to use it. If we have A and B over there, you can see that B dot A. We can also do a different way of doing it is np dot dot A comma B. That does the same thing, but also notice that A dot B and B dot A give you different results. So if we do A comma B, we get those numbers. B comma A, we get these numbers. Let me zoom in. Cool. And furthermore, the order also matters. So this is what I just talked about. A times B is not the same as B times A, but also if I choose to do A times B first and then multiply by C, it's different from doing B times C first and then multiplying it by A. So just things to note as well. Awesome. At this point, any questions? I know that this is a lot of information, so no silly questions, anything at all.
Just real quick, so when you put like B dot A, whatever's in the parentheses is considered the first matrices, correct?
Ooh, good
Or is
question.
it the other way?
Whatever, it is the other way around. Yeah, it's
Okay.
first dot dot second.
Got it. Okay.
Yeah, that's a good clarifying question. Neat. Anything else? Okay. Just really quickly to talk about cross product. It is used for very abstract applications of linear algebra. So for here, we'll just define it for vectors. You will never have to do a cross product of anything. So just good to know that it exists so that if someone just mentions the term cross product, you know it's just a different kind of multiplication. So the result of the cross product of two vectors is calculated using this. The magnitude of A and B multiplied with each other, multiplied by the sine of the angle formed between two vectors multiplied by n, where n is the unit vector perpendicular to the plane formed by two vectors. Now, what does that mean? So imagine each of my arms are vectors, and they just point anywhere in space. And if I'm making two vectors like this, two vectors, you can always form a plane between them. Imagine I put a sheet between my arms. That is a plane formed by two vectors. So a unit vector that's perpendicular to the plane formed by two vectors means that, okay, if I have this plane here, something that's perpendicular to the plane is a vector that sticks out of the plane. And a unit vector means that it has a length of 1. So a lot of things there, but that's what that sentence means. This cross product, this result that you get from doing a cross product, has a magnitude equal to the area of the parallelogram formed by the two vectors. Also a lot, but let's draw that out real quick. So we have two vectors over here. Let's just say, actually, let me use a different color. Let's just say that we have this blue vector and then we have an orange vector here. The parallelogram formed by these two vectors is actually, if you were to duplicate, let me see if I can find out. Oh, I can't do a dotted line. Okay, anyways, if I duplicate each of these vectors like this would be the parallelogram formed by two vectors, this area in between. So the magnitude of your cross product is equal to the area of that parallelogram. It is also going to be perpendicular to the plane formed by two vectors. So again, the cross product is going to shoot out of the vector. And then also when you do a cross product, you lose a dimension. Just facts about cross product. But again, you probably will never come across cross product again. I just think it's in like one lab in your Canvas stuff. Okay, so division, you can't divide matrices. However, you can get the inverse of matrices, and we also from this have to talk about the identity matrix. So it is not possible to divide by matrices. However, broadcasting still does work element-wise, but what we can do is find the inverse of a matrix. So how do we define an inverse of a matrix? When a matrix is multiplied by its inverse, it results in the identity matrix, and that's how you define the inverse. So the order of multiplication doesn't matter when you have a matrix and its inverse. So we talked about matrix multiplication earlier, where order does matter. When it's the inverse of itself, you get the same result. That result being the identity matrix. So what is the identity matrix? An identity matrix looks like this. It's just any square matrix with a diagonal of number ones across its main diagonal. So from top left to bottom right. When a matrix is multiplied by an identity matrix, it will result in the same matrix itself. So it's kind of like the operational equivalent to 1. So like if you had a 3x3 matrix and you multiplied it by this, you get the same 3x3 matrix. If you work out the matrix multiplication, it gives you the same matrix back. So just to prove that that is true, if I have this matrix X, which is this over here, and then I also have the identity matrix, which NumPy actually has a function for creating identity matrices, which is over here. If I take the multiplication of both, you result in exactly the same thing. So identity matrix, basically like the number 1 in math. So taking a look at inverse, so you don't have to learn how to calculate the inverse of a matrix. There are actually ways to figure that out, but it's a very tedious process. So you don't have to do that because NumPy has that function for you. So here you can see that I'm just using the inverse of X, and what I'm printing here is this is the inverse of X. And if I multiply X, and if I multiply the inverse of X by X itself, which is what I'm doing here, X dot inverse of X, of course I'm rounding it off, you end up with the identity matrix itself. I mean, you have some like negative zeros, but negative 0 is 0, but this is the identity matrix itself. So just to show that, a matrix by its own inverse multiplied by its own inverse gives you the identity matrix. Cool. Any questions about any of these operations before we talk about more complicated math? Sweet. Okay. So next, let's talk about systems of linear equations. So you might have encountered this before. I think some of you in math might have encountered this before, but it's actually a very, very common way of solving systems of linear equations using linear algebra. So what is a system of linear equations? It's linear equations that only have linear variables. That means whatever unknown values that you have are only multiplied by a scalar and raised to a power of 1. For example, these are linear equations. X minus 2y is equal to 1. Your unknowns being x and y. X is only multiplied by 1. Y is multiplied by, I guess in this case, you would say -2. And even this one, E is a constant number, so it's a scalar technically. So is pi. So 2 pi and 3e are both scalars. So this is also a linear equation. Now these are not linear equations. Here you can see x squared. Once you have x squared, that's no longer linear. Also, the log of y makes it nonlinear. If you have y to the power of x, it's definitely not linear. And if you have the exponent, that's not linear either. So if you remember, when we did our linear regression, our resulting equation is a linear equation because we're looking at linear relationships between your variables. Even when you did some sort of transformation, you log transform your variable, your unknown will become the log of it. So you're kind of, when you were looking at the relationship of between a logged variable and your target, it's still a linear relationship. So it's still a linear equation. I hope that made sense. But okay, let's just say that we have this system of linear equations and we want to find x and y. Of course, the algebraic way is, you like move the equations around and you substitute in like the values of equations, you end up with values of x and y. But we can do this a matrix way, which we'll actually scale up to solve linear regression in the next section. So first we have to think about how do we represent these equations as matrices or vectors. Let me zoom in even more. Okay, so representing it as matrices and vectors, this is how we do it. We just take the scalar values here. So x and -2, 1, -2, 3, and 2, put them into a matrix. We put x and y outside like this, because if you were to do the matrix multiplication here, it actually works out to give you this again. And then the other side of your equation, just the one in the row. So how do we solve this? Basically, we solve it through this system series of steps, which I'll walk through. So let me first define these, but we'll walk through this. So let's just call this square matrix A and this vector B. So what we start with is A multiplied by X, and X we'll just use to define the vector of our unknowns for now, equal to B. So we're going to use a bunch of things that we have learned over the past half hour to work through these equations. So first, let me get this drawing up. Okay. So first we have A multiplied by X equals B. That's literally what we have here. This is A, this is X, and then this is B. If you remember for algebra, in order to solve for X, we want to move everything to the other side of the equal sign. So what we want to do is we want to take A and somehow move it to the other side. But remember, we can't do division. So instead, what we do is we multiply it by the inverse, which is kind of like division. So what we do here, you can see that we're taking the inverse of A multiplied by A. And remember that we're putting the inverse on the left side because the order matters. So we're putting the inverse of A over here. Therefore, we're also doing the same thing on the other side. And eventually, these cancel out. Becomes the identity matrix, which is pretty much just 1 times. And then we're left with this. So how we solve for X is we're just multiplying B by its inverse, by A inverse on its left side. Cool. So if we do all that, and I actually have the code over here, if we do all that, let me get rid of these drawings. We end up with an array of 3 and 1, which is neat because that corresponds to our X and Y values. So just to check if that tracks, X is 3, Y is 1. Okay, let's see if that works out. So X is 3 minus 2 times 1 gives you 1. Cool. 3 minus 2 is 1. Here X is 3, so we have 9 plus 2 times Y, so that's 2 is equal to 11. Cool. We solved the system of linear equations. And all we did was take the inverse of this matrix and multiply it over here. Cool. Questions about this stuff? Because we're about to scale this up for linear regression. Mm-hmm.
So because you're multiplying by the inverse times X, it's just going to be X itself. So we can just kind of disregard it, correct?
Yes, exactly. Okay. So yeah, these, you can sort of think of it as like they cancel each other out. But really, they become the identity matrix, which is basically like multiplying something by 1. So yeah, essentially, you disregard it. Yes.
Okay. Thank you.
Anything else? You're welcome. All right, let's move on to linear regression. So a linear regression can be interpreted as the solution to a system of linear equations, where each observation corresponds to a linear equation, and the coefficients are the linear unknowns that we're solving for. So just to think of that and say that again, each observation is a linear equation. So, and we have an example that we're going to work through in a little bit, and the coefficients are what we're going to solve for. So each observation is represented as a linear combination of features. So our prediction equation, and we know this already, looks like this, right? The predicted y is equal to your intercept plus some coefficient times value plus coefficient times value plus coefficient times value. That's what we were doing at the end of last phase. So if we represent this in matrix form, we're going to see this as y equal to x times b. B being our beta coefficients, and x being all of the data that we have, and y being all of our, think of that's our like our y train, our target variable, basically. So let's work through this problem with the miles per gallon data set. So what we're doing is we're going to predict miles per gallon using all of these variables. And we've done a bunch of examples with this last phase as well. Okay, so to think of it like this, we're trying to find some sort of coefficients that will help us create an equation of miles per gallon equal to something times cylinders plus something times displacement, something times horsepower, something times weight, basically coefficients. So let's just do all of this splitting up. We have just our x's and our y's. So we have our xdf over here, and we're going to add this intercept term. Hold on, let me just run this cell so I make sure that we have them. Okay. This constant term, I'll explain in a little bit. Adding this constant basically allows us to get our intercept term. So cool. If I want to illustrate what we've just done, we have our y train. Oops, what am I trying to do? Okay, we have our y train, which is like is one column of our data frame. This is our y train. We also have our x train, which would look like this. You know, you have some features, a bunch of rows. On the other hand, we also want to solve for our coefficients. Our coefficients will be the same length as the number of columns here. So it'll look something like that. And this red length is the same length as that. We want to solve for our coefficients. So very, very similar to what we had earlier, right? We want to solve for this. And if I just label them, this is our y, and this is our x, and this is our b. We want to solve this linear algebra equation. So cool. Now that we know how to do this, because we did a very small example before, we want to just isolate beta, because beta is what we want to solve for. So cool. From the last time that we did this, all we did is we multiplied x inverse on either side over here. So that means that if we want to solve for this, beta should be equal to x inverse multiplied by y, right? That logic tracks. Cool. Let me scroll down a little bit and run this next cell. Okay, so x inverse, let's try to do that. We take the x inverse, we get an error, and let's read that error message. It says that the last two dimensions of the array must be square. So we run into an issue. We can't take the inverse of x. Why is that? Because since we can't find the inverse of x, we can't solve this the same way that we solved our smaller system of equations. So basically, if we go into a little bit of linear algebra theory, just bear with me for a little bit more theory before we continue on. Inverse has to be a square because in linear algebra theory, we have this concept of an invertible matrix, which is always a square matrix that has an inverse. So n by n square matrix is invertible if there exists another n by n square matrix B such that A times B, B times A is the same equal to I. So by this definition, we can only find the inverse of square matrices. So we're kind of at a standstill here. So with B not being square, how can we then solve this system using the data that we have? This is the answer to that, this equation over here. So let's figure out how we got there. Okay, so what we started with was, let me get my drawing pencil back. All right, what we started with was y equal to x times b. And we now know that we can't just simply take the inverse of x. However, there's a way that we can sort of force x to be a square such that we can take the inverse of it. And how we do that is we actually take advantage of its transpose. So what we're doing is we're going to first add a transpose on either side. So x transpose y equal to x transpose x times b. So it looks like we made it a little bit more complicated, which we did. But now this result is a square. When you do matrix multiplication, let's say you have dimensions a times b. And remember how I said earlier, these inner dimensions have to match. So I have b times c. When I do this multiplication, again, these have to match. The result is going to be a times c. So if these are transposes of each other, and this is b times a and a times b, this will naturally become a square. So that's why this results in a square. So now that this is a square, what we can do is we can actually take the inverse of that whole thing. And so that's where it gets a little bit scary looking, where you have x transpose x inverse multiplied by x transpose y equal to basically x transpose x. Oh, my handwriting is getting uglier, but x transpose x times b. That's how we end up with this, but these all cancel out. So we have b isolated on its own right now. This what we have over here matches this equation over here. So we basically made use of the transpose, we made use of the inverse to solve for b. And all we have to do really is just plug in all of our numbers in matrix form or in data frame form into this equation, and we can actually get our coefficients. And we're going to see that right now. So back to my mouse. Okay. So I've sort of broken it down into different steps so you don't have one long line of linear algebra equations. But what we have here is x transpose, which works. We are taking the, oh, by the way, np.matmul is the same as np.dot. I don't know why they have two functions for the same thing, but they do. But this is x transpose times x. You're taking the product of x transpose x inverse and x transpose, that's this part over here. And finally, we multiply it by y. When that's done, we end up with these coefficients. And great, all we have to do is these will correspond to the columns of the x data frame. And if we zip them together, we have, this is the cylinder's coefficient, displacement coefficient, these are the coefficients, and this constant one, that is the y-intercept. If we want to compare it to scikit-learn, which we will do right now, you'll see that the numbers match up. The constant or the intercept is negative 14.535, cool. And the coefficients, you can see that this is 0.329, this is the negative one, so 0.329, 329, 7678, 7678, and I think the numbers will match up to a certain point. But for the most part, the coefficients work out perfectly. So that is actually the method of how stats models solves for your linear regression. It actually does a linear algebra method of solving, which is really neat. To contrast that, and to also preview what we're talking about tomorrow, is scikit-learn actually uses a gradient descent procedure, which is very similar to what y'all did in your pre-work, which we'll talk about tomorrow as well, conceptually, of course. But yeah, two different methods of solving. With small data sets, you usually end up with very, very similar numbers, probably almost the same, probably down to like the 20th decimal place. But yeah, this is how stats model solves your linear regression using linear algebra methods. Cool. In additional resources before we end off, this is a really good playlist, 3 blue, 1 brown. I don't know if this link still works, but if you look up 3 blue, 1 brown linear algebra, it's a really, really good breakdown of linear algebra, but it is like a few hours worth of videos. But highly recommend if you ever wanted to do a deep dive. This walks through a step-by-step matrix approach to linear regression. Basically, they have more time to talk about this process that we just did. Fun interactions, good video on explaining scalars and vectors, and also interpreting what this actually means. But yeah, that's all I have to share for today in terms of linear regression. I love talking about linear regression. It's probably like my favorite part of math. So if anyone wants to talk about it, let me know, we can talk about it. But yeah, any questions at this point?
Yes, one quick question. So when we do the transpose, right, we just need to put as a dot T, or like
Yes.
any other methods are there?
So dot T works. Let's see, x df dot T works. You can also do dot transpose. It does the exact same thing. I think it's like this. Yeah, dot transpose also works.
Okay. Yeah.
Mhm.
And one more thing, when we because it takes only the square part of it for right.
Inverse. Right?
So instead of the inverse part, like so we just take the x all the time for transpose, or we can transpose both?
Ah, you mean why do we do this over here?
Yeah.
Yes, it's because it's not square. We have to multiply it by the transpose first. So we do, so let's see, if I do this, x transpose x. So this is x transpose x, and if we do dot shape, oops, dot shape doesn't have that. X transpose x is a 7 by 7 matrix. So
Okay.
therefore now this is a square, we can take the inverse of that.
Okay. And like, so why would not get transposed, right? Or why can get transposed?
Oh, yeah, y won't be transposed, no.
Yeah. Okay.
Because you don't really need to do anything to y, I guess. I guess it's just how the equation is. You don't have to do anything to y.
Yeah. Okay. I think that's because like the same way Excel also has transpose. So right, when you pull from there and then like use it for the pivot tables, I mean, you do pretty much similar thing.
Yeah, you do. Yeah, you're right. And interestingly, like the reason why, so I talked about this in object-oriented programming, right? Like when you have parentheses, it's a method. So transpose is a method, but this is an attribute. Dot T is kind of like an attribute because it's the same data, just you're turning rows into columns, columns to rows. So it's kind of like an attribute. You don't have to do much computation, which is just fun tidbit to know.
Yeah.
Cool. Anything else? Awesome. Well, tomorrow, same time, we're going to be talking about gradient descent. I'm going to do like an overview of calculus of like what's important. And I'm going to do it's going to be fairly big picture of how gradient descent works and how to think about gradient descent and yeah, arriving at optimal values, which is the scikit-learn way of solving linear regression, which is neat. And actually scikit-learn, which we'll be using for the rest of this phase as well. Almost every algorithm that uses gradient descent, almost every algorithm we're going to talk about, and if there are exceptions, I'll mention as well, they're going to be using gradient descent procedures. So will be neat.
And these resources are all also available in the previous workbooks, right? That you have shared? Yeah. Okay.
They're the same. Yeah. Cool. All right. Well, if there's nothing else, Slack me out if you all have any problems or any questions. And yeah, I will see you all back here tomorrow. Bye, everybody.
Thank you.
Thank you.
Have a good one.
Thank you. Have a
Good
great
night,
night.
everybody.
Okay.